Good morning friends. Up to this we discussed the last numerical of exercise 14.9. We take the data of this exercise numerical 14.9. Take the position of mass when the spring is unstretched as x is equal to 0. Now before it, in 14.9 exercise, one end of that spring is tied with a block of mass m placed on a horizontal frictionless surface, and other end is tied with a Z wall like this situation. That is the horizontal surface. Here the one end of the spring is tied with this. Now block of mass m is placed on a horizontal frictionless surface m. Here the mass of the block is 3 kg. Force constant of the spring is given 1200 Newton per meter, and amplitude A is equal to 2 centimeter. Amplitude is the maximum displacement on either side of mean position. In our question that is given, take the position of the mass when the spring is unstretched as x is equal to 0. There is the unstretched position, so there is the x is equal to 0 position. And the direction from left to right is considered as a positive x direction. Positive x direction. Positive direction of x-axis give the s as function of time. That means we have to derive the equation of simple harmonic motion in 3 different positions. Time t for the oscillating mass. If at the moment we start the stopwatch t is equal to 0, the mass is at first the mean position. At this time, this position, time t is equal to 0. What should be the equation of displacement? That means the simple harmonic motion. Second, at the maximum stretched position, and third, at the maximum compressed position. In what way do these functions for simple harmonic motion differ from each other in frequency, in amplitude, or the initial phase? Okay. Now, here the amplitude is given at 2 centimeter. Therefore, the maximum we can stretch, the maximum displacement of a block M at here, that is the x is equal to 2 centimeter distance. There is a maximum stretched position of a block, and maximum compress is this. There is also x is equal to 2 centimeter in this side. So first, second, and third position we have to derive the equation of the displacement of a simple harmonic motion. We know that the equation of the displacement of a simple harmonic motion, x is equal to a sine or the cos, right? Omega t plus phi. Phi is the initial phase, omega is the frequency, and a is amplitude. Amplitude is already given. We require the angular frequency. And on the position of this, we can find out the initial phase. Clear this? Okay. So first part A. First we find out the angular frequency of oscillation. Angular frequency of oscillations. Omega is equal to under root of k upon n. K is given 1200, mass is given 3 kg. Clear this? Okay. Therefore, square root of 400, and that is the 20 radian per second. That is the angular frequency. Now, first part A, at mean position. At mean position. Now at mean position, initial phase, phi is equal to 0, and displacement and anytime t is given by the equation x t is equal to a sine omega t plus phi. We substitute the value of a, omega and phi. A, omega and phi. A is 2 centimeter. Sine here omega t plus 0. Omega t plus 0. Therefore 2 sine omega t, that is in centimeter. So that is the equation of simple harmonic motion at mean position at any instant of time t. When this block is oscillate about their mean position, the equation of simple harmonic motion at mean position at any time, initial time or any time t, is represented by this equation 2 sine omega t centimeter. Okay. Now B is that at maximum stretched position, at maximum stretched position. Okay, in this condition, initially start its position oscillation in this direction. So that is the first point. So here its phase is pi by 2. Its phase is pi by 2. That means at x is equal to 2 centimeter point, phase is phi is equal to pi by 2. Pi by 2 radian. And displacement at time t is x t is equal to a cos, a sine omega t plus phi. This substitute the value a is equal to 2 centimeter sine omega t, omega is 20. Omega is 20. 20t plus phi pi by 2. Now we know that sine pi by 2 plus theta. So there is in second quadrant sine is positive, and pi by 2 plus theta, sine pi by 2 plus theta is equal to cos theta. Using this concept, we can write 2 sine. Sine is converted into cos, 2 cos 20t centimeter. That is the equation of displacement at this position. Now see, at maximum compressed position, phase phi is equal to 3 pi by 2, because there is the pi by 2, again pi by 2, again pi by 2. So 1 times, 2 times and 3 times. So 3 pi by 2 phases. And displacement is xt is equal to a sine omega t plus phi. Substitute the value 2 sine 20t plus 3 pi by 2. Now 3 pi by 2, that is in third quadrant. Therefore, minus 2 cos 20t centimeter. So that is the displacement. Now here the amplitude of displacement of simple harmonic motion is remain same, but the phase are different, therefore the displacement are also different. Angular frequency are same. So here the phase are different. Phase are different. So only we have to use the equation of simple harmonic motion. Either the x is equal to a sin omega t plus phi or x is equal to cos omega t plus phi. Why we are not using here the cos omega t plus phi? Because initially at time t is equal to 0, the oscillator at mean position, that means the x is equal to 0. Due to that reason, we are using the sine function. If at time t is equal to 0, the block of mass m is at extreme point, at that time we are using the a cos omega t plus phi. Because when you are going to learn this numerical, at that time the question arises in your mind head. Mostly we are using the a cos omega t plus phi function, while we use here the a sin omega t plus phi. So here the solution is that initial position of a block or the oscillator is at mean position at time t is equal to 0. Due to that reason, here we are using the sine function instead of the cos. If the block initially at extreme point, either this or this, in that case we are using the x t is equal to a cos omega t plus phi. Clear? Okay. Now, next numerical 14.11. Here the figure corresponding to the two circular motion, the radius of the circle, the pair of revolution, that means in clockwise direction, anti-clockwise direction, and so on, are indicated in each figure. Now, obtain the corresponding simple harmonic motion of the x projection of the radius vector of the revolving particle p in each case. Now listen, in first figure, where the particle is moving in clockwise direction, this direction. So what is the projection of this particle on x-axis? The projection of particle perform the simple harmonic motion like this way on the x-axis. We have to derive the equation of the simple harmonic motion of the projection on x-axis. That means the x component of simple harmonic motion. In both cases, in figure A, the position of particle P here, and here the particle moving in, or the motion of a particle is in clockwise direction for part A. In figure A, motion is in, first thing, what is the amplitude? Amplitude A is equal to 3 meter. Periodic time T is equal to 2 seconds. Is equal to 2 seconds. Now the motion is in clockwise direction. Motion is in clockwise direction. Right? At time t is equal to 0, particle is at here instead of this. Instead of this. Therefore, initial phase is pi by 2. Initial phase is pi by 2. Therefore, at time t is equal to 0, the particle at P and its initial phase phi is equal to pi by 2. Phi is pi by 2. Now, what should be its angular frequency? And angular frequency is omega is equal to 2 pi upon t. T already given, there is the 2 second, therefore 2 pi upon 2, that means the pi radian per second. Now, we require the equation of simple harmonic motion for x component of particle P. Right? Therefore, equation of simple harmonic motion for x component of particle that is given by our equation x is equal to a cos omega t plus phi. Why we take here the cosine? Because here the particle starts its motion from the extreme positive, x is equal to a position. So from this to this, initially time t is equal to 0, particle at here. Therefore, initial phase is pi by 2. Therefore, we take the cosine function. A is given, there is a phase cos omega is the pi t plus pi by 2. Now, cos pi by 2 plus theta, we know that cos pi by 2 plus theta, that is in second quadrant. Second quadrant cosine is minus, therefore minus sin theta. Minus sin theta. Therefore, minus 3 sin pi t meter. Pi t is in meter because poles are given in meter. So there is a question of x component of simple harmonic motion. X is equal to minus 3 sin pi t in meter or the centimeter. That is depends on A is given in which unit, either meter, so meter, that is given in centimeter, therefore centimeter. Now the next part for figure B. For figure B. In figure B, what is the amplitude? Amplitude is given the 2 meter. Maximum displacement. And periodic time t is given as 4 seconds. Periodic time t is given as 4 seconds. Here the motion is in anti-clockwise. Motion is in anti-clockwise. Anti-clockwise. That means the particle starts its motion from this direction. At time t is equal to 0, particle already the half oscillation is completed. Therefore, initial phase is pi. Initial phase is pi. Motion is anti-clockwise, and at t is equal to 0, the particle at p. Particle at p. And its initial phase is phi is equal to pi. Phi is equal to pi. This and this. Pi by 2 plus pi by 2, that means the pi. And angular frequency what is the angular frequency for this? Omega is equal to pi upon t. Here the t is given the 4 seconds, therefore 2 pi upon 4, that means the pi by 2. Radian per second. Radian per second. Now, equation of simple harmonic motion. Equation of simple harmonic motion for x component of p. X component of particle p. Particle is x is equal to a cos omega t plus phi. A is already given to cos. Omega is pi by 2 into t plus phi. Phi is the pi. So it's equal to cos pi plus pi by 2. Cos is in which quadrant? Third. Pi plus pi by 2 plus into t. Therefore, 2 sin pi by 2, that is minus. Minus 2 sin pi by 2 into. So that is in meter. X is equal to minus 2 sin pi by 2 into t is in meter. Clear? Now friends, the next numerical is 14.40. Here the figure A shows a spring of force constant K clamped rigidly at one end and a mass M is attached to its third end. Now figure A is given. The one end of the spring having the force constant K is connected with a rigid support, while the another third end of the spring is connected with the body of mass M is placed on frictionless horizontal surface. Right? A force F is applied at the free end and stretches the spring. Right? While figure B shows the same spring with both ends free and attached to a body of mass M. At either end, each end of the spring in figure B. That means here in figure B, the same spring, the same spring is placed on a horizontal surface. At the both free end, the block of mass M, equal mass, are tied. Now we apply the equal force F on both this body. At that time, first we have to find out what is the maximum extension of the spring in both cases. What is the maximum extension in spring due to the applied external force? Second, if the mass in figure A and two masses in figure B are released, so what is the period of oscillation in each case? Now listen here. First we pull apply the external force and we increase the length of the spring and we release. So it performs the oscillation. We have to first find out what is the extension in length of the spring and what is the period of oscillation. Now here, yes, we apply the same force on both block of mass M. So what should be the extension in the length of the spring? And yes, we release the both block. So both perform the oscillation about their mean position. What is the periodic time? Also in figure. So first we describe for the figure A. In figure A, suppose acceleration of mass M is A, or the A is acceleration of mass M, and due to force F, the extension in a spring is Y1. So from Newton's second law, F is equal to M and restoring force F is equal to minus Ky1. Y1 is the extension in a spring. Already we assume that. And the extension in a spring is Y1. Therefore, here we substitute the value. Therefore, Y1 is equal to, from this equation, Y1 is equal to F upon Q. Is the increasing is maximum extension in a spring. Clear? Okay. That is the equation 1 and that is our 2. Comparing equation 1 and 2. Compare equation 1 and 2. So we obtain MA is equal to minus Ky1. Therefore, acceleration A is equal to minus K upon My1. That is the acceleration. Equation. Now, acceleration for simple harmonic motion is A is equal to minus omega square 1. Equation 4. Therefore, from equation 3 and 4, that means the comparing equation 3 and 4, omega square is equal to K upon M. Omega square is equal to K upon M. Therefore, omega is equal to square root of K upon M. Square root of K upon M. But we know that the period of oscillation T is equal to 2 pi upon omega. Therefore, T is equal to 2 pi under root of M upon T. That is the period of oscillation for figure A. For figure. Now, for figure B. For figure B. Applying force on both body. Applying force on both body. The extension in each body or each gas is wide. Therefore, total extension each side is wider. Total extension y2 is equal to y dash plus y dash. That means the 2y dash. Now, F is equal to ME and destroying force F is equal to minus K into 2y dash. 2y. Therefore, y dash is equal to F upon 2. Is the extension in each spring. Clear this? Now, acceleration A is equal to, or the MA is equal to minus K into 2y dash. Therefore, A is equal to minus K upon F is equal to, so here we compare F is equal to MA and F is equal to minus K into 2y. Yes. Therefore, acceleration is equal to minus 2K upon F. 2K upon F into y. Compare with acceleration A is equal to minus omega square 1. Therefore, omega square is equal to 2K upon M. Therefore, omega is equal to under root of 2K upon M. And periodic time T is equal to 2 pi under root of M upon 2K. There is the period of oscillation of both the body in figure C. Right? So, here only we have to first write down the Newton's second law and also whatever the strain force is produced in both cases. After that, we can find out whatever the extension in the spring. And now comparing these two equations, we calculate the acceleration and we compare this acceleration with the acceleration for simple harmonic motion minus omega square y. Therefore, omega square is equal to 2K upon M. Therefore, omega is equal to under root of 2K upon M. But period of oscillation T is equal to 2 pi upon omega. Therefore, 2 pi into under root of M upon 2K. Clear this? So, there is the solution of this numerical. Question of numerical is quite lengthy, but here the solution is very easy. Next numerical 14.14, earlier is 13. Now the piston in the cylinder head of a locomotive has a stroke twice the amplitude of 1 centimeter. If the piston moves with simple harmonic motion with angular frequency of 200 radian per minute, what's the maximum speed of a piston? Now first thing, what is the stroke? Stroke, that means here the in piston cylinder arrangement, here the cylinder is moves up and down, up and down. So there is the maximum displacement from initial position to this direction is 1 centimeter is given. But our definition of amplitude is that the maximum displacement on either side of mean position. Mean position is here. X is equal to 0. So amplitude is half of the centimeter or half of the displacement, half of the stroke. Stroke, that means the distance between the minimum position and maximum position, this way. Therefore, the amplitude is the half of the stroke. Therefore, amplitude of a piston moves with simple harmonic motion, Just me. Amplitude of a piston moves with simple harmonic motion is A is equal to half centimeter, that means the 0.5 centimeter, and angular frequency of a piston. Angular frequency, actually that is the angular speed. Omega is given 200 radian per minute. Right? Therefore, what we have to find out, the maximum speed of a piston. Maximum speed of a piston is V is equal to A into omega. Now listen, actually there is the relation between the linear speed and angular speed. We learned about this relation in rotational motion. At that time we obtain V is equal to R omega. R is the radius. Here instead of the R, A, there is the amplitude. Now we substitute the value. So there is the 0.5 into 200 radian per, that is given the radian per minute, therefore there is the centimeter per minute. Convert into centimeter per second, therefore 0.5 into 200 upon 60. That is the centimeter per second, or in other words, 100 by 6 is equal to 1.67 centimeter per second. So that is the linear speed of a piston that moves up and down in a cylinder. Actually, that is the engine of our vehicle. How the vehicle performs the linear motion due to the oscillation of a piston in a cylinder. So a piston moves like this way in 1 centimeter stroke. Therefore, the amplitude is half, and linear speed of a piston is 1.67 centimeter per second. Clear this? Okay. Now the next numerical 14.15 here. In next 14.15, the acceleration due to gravity on the surface of the moon is 1.7 meter per second square. What is the time period of simple pendulum on the surface of the moon? If its time period on the surface of the earth is 3.5 second is given. For that purpose, the periodic time of a, suppose, time period on the surface of the earth is 3.5 seconds. That means the TE is 3.5 seconds. And on the moon is TM. We have to find out this. Now for moon and earth, value are given on the surface of the moon, GM. Acceleration due to gravity is given 1.7 meter per second square. On the surface of the earth, there is the 9.8 meter per second square. We have to find out the TM. TE is given, that is the TE, 3.5 seconds. Now, time period of a simple pendulum is T is equal to 2 pi under root of L upon G. But here the length of the pendulum is constant, but L is constant. In both cases, that means on the surface of the earth and also on the moon, the L does not change. Therefore, T proportional to the 1 upon under root of G. The periodic time of a simple pendulum is inversely proportional to the square root of gravitational acceleration. And due to that reason, now, on earth, TE proportional to the 1 upon under root of G, and on moon, TM proportional to the 1 upon under root of G. We require the TM, therefore TM upon T is equal to under root of GE upon GM. Taking the ratio of TM upon T, we obtain square root of G upon GM. Therefore TM is equal to T under root of G upon GM. T is given 3.5, under root of G 9.8, GM 1.7. 9.8, okay, 1.7. Therefore, the TM is equal to 8.4 seconds. Check it. Calculate yourself. So generally this type of the numerical is asked in exam. Here the time period on the surface of the earth is already given 3.5 seconds. We take this pendulum on the surface of the moon. On the surface of the moon, gravitational acceleration is 1.7 meter per second square, while on the surface of the earth is 9.8 meter per second square. For the same pendulum, the periodic time on the surface of the earth is 3.5 seconds. We have to find out what is the periodic time of this pendulum on the surface of the moon. Now, the time period of simple pendulum T is equal to 2 pi under root of L upon G. Here, the time period is directly proportional to the square root of length of a pendulum and inversely proportional to the square root of gravitational acceleration of the surface. Here, the length of a pendulum is constant in both cases. Therefore, T is proportional to the 1 upon under root of G. Therefore, using this equation, what is the equation of periodic time of the simple pendulum on the earth? TE proportional to the 1 upon under root of G, and on the moon, TM proportional to the 1 upon under root of G. We require the TM, therefore taking the ratio of these two equations, TM upon T is equal to under root of G upon G. Therefore TM is equal to T, take this T in this side, into under root of GE upon 0 is equal to 3.5 under root of 9.8 upon 1.7. Therefore, we obtain the Tm is equal to 8.4 seconds. So this type of the numerical already we discussed. Find the length of a second pendulum. For second pendulum, the periodic time T is equal to 2 seconds. Right? At that time, we also use this expression T is equal to 2 pi under root of L upon Z. Clear? Okay. So here this chapter is completed. Whatever the numerical are important for us and also for 12th standard and competitive exam, we discuss only those numerical. Not we consider the much more, that means the all the numerical of illustration and also the exercise. Clear this? Only that is your syllabus what we have discussed in these lectures. Numerical and plus theory. So here this chapter is completed.